Alrighty then. Okay, counting principles. Permutations and combinations. So combinations are different from permutations, but they call combinatorics is any branch of math dealing with ways to count in complex situations. So these techniques are also valuable for probability calculations, which you'll learn in the next unit, because Unit 3 is about probability. When you have to make a series of choices, you can usually determine the total number of possibilities without actually counting each one individually. So just to give you a little example, let's say I have 4 shirts and 3 pairs of pants. How many possible outfits could I wear? Huh? 12, right? Because you have 4 choices here and 3 choices, so I have 12 choices of outfits. Because if I pick my blue pants, I have 3 shirts I can wear with that, or if I pick my red pants, I have 3 shirts I can wear with that. So that's an example of how we're going to be counting. We count our choices. So there's 4 choices for the pants, 3 choices for the tops. When you have to make, I said that already. Okay. This is the fundamental counting principle. If a task or process is made up of stages with separate choices, the total number of choices is m times n times p, where m is the number of choices for the first stage, that could be your pants, n is the number of choices for the second stage, that could be your tops, and p is the number of choices for the third stage, that could be your shoes, and so on and so on and so on. So that's the fundamental counting principle. Okay. We'll just, and you'll see me use FCP just for short. Fundamental counting principle, just use that for short. Okay. So some of the things you need to realize before we do the additive counting principle, like I wear my pants, my shirt, and my socks all at the same time, right? That occurs at the same time. So what we say is stages or actions occur at the same time. Or together, right? The additive counting principle states if one action can be performed in m ways, before I continue, before I forget, the way to distinguish between the two 99% of the time is you'll see an and. I'm going to wear pants and a top and some shoes, right? You'll see this word and in the question. Okay. If one action can be performed in m ways and another action can be performed in n ways, and they cannot be performed at the same time, right? That's where it's different from this. These actions can occur at the same time, and stages or actions cannot occur at the same time. Like when you roll a die, you either roll a 2 or you roll a 3. You can't roll a 2 and a 3 at the same time because you're only rolling one die, right? Then, in this case, we add them. Then there are m plus n ways in which either the first action or the second action can be performed. What you'll see is in this type of question, 98% of the time you'll see a or. You either roll a 2 or a 3, right? And then you know there's only one way to roll a 2 and one way to roll a 3, and the total number of ways to roll a 2 or 3 is 2. Simple example, but we'll do lots of examples. So again, this principle is used when actions cannot occur at the same time. Okay. Okay? It's one or the other, not both. So the results are added together, and I will demonstrate that, okay? Let's look at this. So why don't we, just for short form, we'll call this the additive counting principle. And so additive counting principle involves adding, while fundamental counting principle involves multiplying. Suppose there are three towns, A, B, and C. There are 3 roads from town A to town B, 1, 2, 3, and 2 roads from town B to town C. They want to know how many routes are there to get from town A to town C. Well, are we going to be using the fundamental counting principle here or the additive counting principle here? Huh? Fundamental counting? Why do you say that? I'm not saying you're right or wrong. I just want to know your reasoning. Okay, because you're going from A to B and from B to C, right? This is all, even though you have to go to B before you go to C, because we're really going from A to C, we consider this to be happening at the same time, right? Because we're going from A to C, we have to, so it's not additive, it is count. It is the fundamental counting principle. So this is going to be, how many ways are there? Well, we go 3 times 2 equals 6 ways to get from A to C. To get from A to C. So far, so good? So you could go you could do this. That's 1 way, 2 ways, 3 ways, 4 ways, 5 ways, 6 ways to get from A to C. Alright, let's keep going. At a private school, students wear school uniforms. Each student must wear either a white dress shirt, a blue dress shirt, or a white golf shirt. How many choices do we have on the shirts? Great. So it's one white shirt or one blue shirt or one golf shirt. So inside here we add them up because within the shirts that's the additive counting principle. But when we start combining shirts with pants, how many choices do we have on the pants? Wear dress pants in gray, black, navy, or white. So how many choices on the pants? And then we have shoes must be either black or blue in loafer or lace-up style. So we could have loafer black, loafer blue, lace-up black, lace-up blue. How many choices on the shoes? Now we have socks, right? So it could be the socks. 1, 2, 3, 5 choices on the socks. So notice all of this, we're wearing this all at the same time, so it's the fundamental counting principle overall, and that equals 240 different uniforms.
On a test, will we have to show that when you're choosing shoes, we have to use the fundamental counting principle because it's a choice. It's a choice layered within that choice.
Oh, this no, for here no.
For the shoes, you know how you do 4. You can get that either by 2 plus 2 or 2 times 2. And
If you show 4, I'll be happy. in that kind of question, that's enough, yeah. If you show it like this, you don't have to go, if you just showed a 3 here, like on a test, for maximum communication marks, if you showed a 3 here, if you show shirt, your choices, and you put 3, 4, 4, 5 in your answer, I would be perfect. That's a lot of communication happening there. You're telling me where you get the 3 from, where you're getting the 4 from. It's good. A company makes gloves that are black, brown, gray, or burgundy. Each of the 4 colors is available in small, medium, or large sizes. How many different types of gloves are there? So first you're choosing a color, and then you're choosing a size. Right? So the color and size occurs in a glove at the same time, right? Either have black, large, or burgundy, medium. So there are 1, 2, 3, 4 choices on the color, 3 choices on the side, so there are 12 different gloves. How many ways? Oh, either or. That's a hint there that we're now using the additive counting principle. How many ways are there to select a card which is either a red face card? Now red face, if you're familiar with cards, I don't know if I have a set of cards here. Do you know what the faces are considered to be?
Diamond, spade, diamond.
Those are the suits.
The faces.
That's a black face. That's a red face. Okay? Then there's these face cards. And jacks. Fair enough? How many red face cards are there? 6. Okay, so the king, the queen, the jack are the faces. The hearts, the diamonds, the spades, and the club, those are the suits. So we want red face cards. So either a red face, so maybe just to help you out, you have a king of hearts and a king of diamonds. You have a queen of hearts and a queen of diamonds. And you have a jack of hearts and a jack of diamonds. There's 6 of those. Now it's or. You're only pulling out one card. It's either a red face card or you're pulling out a black ace. How many black aces do we have? So how many choices do we have in total? A black ace is going to be an ace of clubs and an ace of spades. And that equals 8. You have to get comfortable with cards in this unit, okay? Because we're going to do poker hands. Okay. Tim tosses 4 coins, one right after another. A tree diagram really helps us in our counting. Okay, so it says here, use a tree diagram to illustrate the results of this activity, and then we'll use the fundamental counting principle. We want to calculate the number of possible outcomes. So we have 4 coins. We're going to toss them. On the first toss, you either get a head or a tail. Right? This is, I'll write my toss number down here. This is toss number 1. So if you, yeah, absolutely there. Okay, so on, if I get a head on the first toss, I could get a head or a tail on the second toss, and I could, if I toss a tail on the first toss, I could get a head or tail on the second toss. So that's toss number 2. So you can imagine this is going to be going, it's going to get a little bit tight here. HT, HT. So this is my third toss, and then we have HT, 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 HT. So notice there are 16 outcomes. We will not list them all. If you were to count this, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's 16 outcomes, and they are like H, H, H. H is one outcome, right? And you could have H, H, H tail is your second outcome, etc., all the way down to tail, 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 tail. Okay? There's, yeah. In this case, yes, order does matter because it makes a difference if you get a head before a tail or a tail before a head. It makes a difference, yeah. Notice how, I guess, HH. Here we have one tail and 3 heads. Here we have one tail and 3 heads, but that's counted once and that's counted twice. So order does matter, yes.
The question says he tosses 4 coins one after another, so order matters. If he tosses the 4 coins at the same time, then order doesn't matter.
Yeah, you're adding in a technical difficulty that doesn't really, that's not an issue in this question. But if you throw them at this, it depends. It depends. I think you can see here order is important. It all depends on how the question is worded.
Yeah, because it says to count the number of possible results. If order does matter, then there are 16 outcomes. But if order doesn't matter, there are only 4.
Yeah, I agree. Well, are there only 4?
Does it tell us to use the fundamental counting?
Okay, you could have. So how many do you have? You could have 4 tails or 4 heads, right?
3 tails, 1 head. 3 head, 1 tail, and then 2 tails.
Yeah, I agree with you. If order does not matter, I agree with you. Okay. One way you can tell here is 4 coins one after another. Yeah. Yeah, good point. Thank you, actually. Okay, part B. Fundamental counting principle. Well, there's 2 choices on the first toss, 2 choices on the second toss, 2 choices on the third toss, 2 choices on the fourth toss for 16 tosses. That's number 1, number 2, number 3, number 4. Yep.
Cases like these where each subsequent choice has the same number of possibilities, like 2 choices, heads or tails, why don't we just do the number of choices to the exponent of how many ever, like,
Yeah,
is
absolutely.
that
Yeah, it's acceptable. Yeah. So again, we get 16 outcomes. Is that okay? Can I flip it over? Okay. Now let's get into more complicated questions. We have 2-digit positive integers. Remember, we're always working with 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 0 to 9, we have 10 digits. We're working with 10 digits. That's what we always work with. Okay? How many two-digit, like 20, 21, 33, how many two-digit positive integers are there? So one thing you need to realize, the first digit cannot be 0. First digit, because if the first one is 0, you really only have a one-digit number, right? And you want a two-digit. So first digit cannot be 0. So how many choices in our digits do we have for the first digit? 9. And for the second one? Equals 90. So there are 90, and you need to write something. Don't just go 9 times 10 equals 90. You have to communicate something. You just say 90 two-digit numbers. Right? People just want to, and I notice on a test, especially in permutations and combinations, they just want to slap down the numbers and that's it. History. Game over. You need to explain. At least something. There's no hard and fast rule, but you should, do your concluding sentence. And if if you write things like first digit can't be 0, it just tells me a lot. How many two-digit positive integers are there where the digits are not the same? Can you see that you could get a 1, 1, 2, 2, 3, 3, 4, 4? Now what happens if they're not the same? Well, let's take a look. You already know if we want a two-digit number, the first one cannot be 0. All right, so we're down to 9. Now, how many choices do we have on the second digit? Yeah, because now you can use the 0.
Second digit, don't you mean it's 9 as opposed to the normal 10 because
You're down a digit.
You're gonna use the first digit.
See, let's say I use,
use 0, which makes
yeah, let's say I use 1. Let's say I use 1. So 1 is gone.
okay.
Now I can use 0, so now I have 1, 2, 3, 4, 5, 6, 7, 8, 9.
But wouldn't your explanation not, it's not 9 because you can use 0, it's 9 because you've eliminated a choice.
Yeah, yeah.
So
I'm just reminding the reader that now I can use the 0 even. Yeah, yeah. If you want to say that, that's fine.
because
Okay, that's good. Yeah, I hear you. Yeah.
Or you can say that there are 9 choices in question 6. There are 9 choices where it's a two-digit of the same two-digit positive integer with the same digit.
Uh,
So 90 minus 9 is
81.
81.
Oh, okay. Yeah, you could do that.
I don't know which way is.
You could do that as well. Jack suggested, well, you could go, there's 92 digit numbers, and we subtract 9 because there are, you have 9 possibilities where you have the same digit, 1, 1, 2, 2, 3, 3, all the way up to 9, 9. You can do that way as well. Perfect. Yeah, no problem with that. Ah, now they say, how many one or two-digit positive integers are there? So we're going to have this or 2 digits. Oh, yes, that end in 7. Yes, thank you. Thank you. Thank you. I had a momentary relapse there. Okay, that end in 7. So there's only one choice there, right? If it ends in 7, there's only one choice there. And how many choices do I have there?
9.
Yeah, because that can't be 0. So there are 10 one or two-digit numbers. Oh, 10 and subtract starting with 0? Yeah, you could. How many three-digit positive integers have no repeated digits? Why don't you sit right there for now? Alright. How many three-digit positive integers have no repeated digits? Well, let's see. 1, 2. Are all these occurring at the same time? So it's fundamental counting principle. So what do you think? So first one is 9, no 0. How many choices here? Perfect. What is it? I'll take your. What is it? 148. In how many ways can 4 boys and 4 girls be seated alternately? So that means boy, girl, boy, girl, boy, girl, boy, girl. Right? Just like. Or girl, boy, girl, boy, girl, boy. Yeah. Okay. In a row from left to right. You guys are really thinking. 1, 2, 3, 4, 5, 6, 7, 8. So we could start with the boy. Or, as this fine young lady mentioned, 2, 3, 4, 5, 6, 7. It could start with the girl. All right, let's do this. For the first position, how many boys do we have to choose from? Once we're down a boy, how many boys do we have to choose from? Then we're down 2 boys. Right? So 4 girls, 4 girls, 4. Oh, what am I saying? Should be 3, right? 3, 2, 1. And similarly here. Hundred and 1152 ways to.
So you don't have to use all the boys and girls at a time.
What do you mean? Because all 4 boys are being used up here.
It's not like you're just slotting. It's not like it has to be it's like Jimmy, Tommy,
No, because we're talking about sentences, so if we have to use everyone, no matter what, every time, you would start with a boy, and then that would be one way because they have to alternate. And then the second way, the only possibility left is if you sat the girl and everyone sits down. But then if you say 11 or 1,152, doesn't that mean you don't have to use all the boys and girls?
you can use them all just in a different order every time.
And they all
The outcomes in this case, if we look at the outcomes, so this is an example of one outcome. But you could have, let's say your boys are this, A, B, C, D, and your girls are E, F, G, H. So you could have boy, girl, boy, H. Do you know what I mean? So you have, so you are using everybody.
It's just that this time. Okay.
Like there's so many there's 11 and 52 different ways you could line them up, even though they're alternating. Uh-oh, how many different license plates can be made by using 3 letters followed by 3 numbers? How many letters in the alphabet? And you have 10 digits, right, to work with. So we have 3 letters followed by 3 numbers. So you have to think, you have to know a little bit about license plates. Have you ever seen a license plate with AA, BC? Can letters repeat? Yeah, letters can repeat. So yeah.
That's 18,000.
That's all those. So this is equal to 17,576,000 different license plates. Sorry? Can I explain anything better? Anything at all? That's your start to counting. I think you can see these are examples where order makes a difference, right? A different order means the number of outcomes you have is greater than if order is not important. And order, so in permutations, order is important, and this is order important. And this is order not important. So for example, if I want 2 people to help me take books to the book room, I don't care what order they're in. Right? I don't care if John goes before Susie or Susie goes before John. I just want 2 people. Right? So order is not important. Okay. Any questions before I sign off here? If I can sign off, I don't know.